Hi everybody, we're one more lecture to this week and then I'll be looking at standard template libraries next week. But I wanted to make sure we hit things that were going to show up in the labs, just in case the labs were confusing, because they probably will be, and also to make sure that we're ready for the next assignment as well. So I want to look at a couple more data structures. This is something that people spend, it in some computer science programs, they may have three or four different classes on just this kind of concept. They vary these blueprint or these template structures that we can use put in our toolbox, if you will, so that we can use over and over again. And what people expect that you can bring to bear when it comes to programming or solving a problem. So these things have actually come up in my Google interview, my Palantir interview, my CEDIA DAPCO interview, and a bunch of other interviews as well, including the complexity, which we're not going to get into. You might get into that later. You will have an algorithms class, but this is a first pass at things. So last time around, we looked at stacks. We briefly, without looking at the code, looked at queues, and we've been looking at linked lists. We have also talked, let me think, what other things have we done? Oh, we also did a network diagram. So we also did adjacency lists, which that's how we recorded it. We had a pointer to all the other nodes in our graph. So let's look at a couple more things. This is actually a kind of graph. Last time for assignment 2, we had a we had this node object that had a list of pointers to other nodes. This is how we represented a network. Well, a tree is just a special kind of network. It happens to be in a cyclic, as in there's no circles, a cyclic network, and we normally have a root node. So there's a node that starts everything off, called the root, and then from there we go down to another node. Each one of these nodes, especially a binary tree, which is our sort of our favorite kind of tree, goes from there. And if you, the reason it's called a tree is if you turn your head upside down or you draw it the other way around, uh, you have the base of the tree and then it goes up to a bunch of leaves. So here's our base of a tree, and then it starts spreading out, and then it spreads out and it spreads out, and okay, there we go. That looks like a tree. So that's why it's called a tree. Or you could, I mean, they probably could have called the root system if you wanted to, but it's called a tree for that reason. Um, each tree item, so I'm just going to erase that because it's a terrible drawing. Each one of these nodes has two, and exactly two, child nodes. Those child nodes could be empty, but unlike our tree last time around where we had this, array of different pointers, we only have two. It's a left child and the right child. The left and the right child can each have a tree of their own. So if I just cut off this line here, everything below that is completely cut off from the rest of the graph. I can remove chunks of my tree at a time by just pruning an individual child. And this also, by the way, if you hadn't noticed, looks like our hierarchy for how we inherit things, right? We have our, we might have our, oh, darn it. Okay, and then we have rect, and then we have square, and we may have, super rect, and maybe this is a um, non-rect, and this is a circle. Now, if we wanted to, it's not necessarily a binary tree. We can actually add other branches to how we do inheritance. But inheritance ends up being we represent it using a tree. That's the only point I'm trying to make here. A binary tree has exactly two nodes. That's why it's called a binary tree. And it allows us to do some crazy things. Like a binary search tree allows me to do a search really, really, really quickly. Um, it's also a really nice way of organizing my information. And so I can take one side or the other and just, arrange everything. It's a sorted group of elements, I can arrange things in a tree, and then it's really quick to go down. It's actually log base 2 of n steps to go down. Don't ask me how I got to that number. I know how I got to that number, but that's how many steps. It's a lot shorter of a path to find an element than walking down the entire array. We'll actually look at how I got to that number later. So that would be a binary tree. It'll look exactly like we had for assignment 2, just with two nodes. Here's another kind of structure, and this actually ends up coming up in um, for the assignment. And for the assignment and for the labs. So this is not a table of hash. This is a hash table. I always think of hash. I don't know why I always think of hashish, but I always think of hashish when I think of hash tables, or a hash breakfast hash. Uh, it is just sort of a mix. It's not derived from hashish. It's derived from hashing things together, putting things together. Um, and so this itself is a data structure, and it does not look like this. This is a way of mapping an item to a particular position uh, in that is an important point. It may not seem like an important point, but it's an important point. The reason you use a hash table is because it is fast. If it's done right and everything works out, uh, all the stars align and everything like that, a hash table is one of our tools that we can, you go to an interview, you drop the word hash table, and they go, oh, okay, they're fine. So a hash table allows you to take an item. Just give me an item, like a node, like a student object, like whatever you want to give me. I find some way of converting that thing to a number, or at least a numeric representation for that thing, and then I throw it into a hash function. The hash function will map from the item to a number, and that number is where it gets stored. And yes, that was hand waving, so let's actually do an actual view of this thing. So hash tables, actually what I should have, I meant to actually update this one slide before I got talked, and I forgot to. Here we go. Let's go to the library, because the library is also using a hash function. This thing right here, the Dewey Decimal System, or whatever system that we are using in the library right now, or any library you go to, there's a unique number on the back, or a set of letters and numbers on the back that they stick on every single book in the library. What is that used for? Right? I'm assuming you know what that's used for. I'm really hoping you know what that's used for. Otherwise, I weep for humanity here. Right? That is to uniquely identify where to store that book. And when you need to find that book, that's the number that you look to find that book. That is actually what a hash table is. That's pretty much all a hash table is doing. But how do I go from a book titled, um, I don't know, The Art of Programming, right? How do I go from a book title like that to a position in the library? Well, I take the book title. I to figure out what the subject of the book is. I figure out who the author of the book is, and that uniquely identifies. So I can have subject, author, and title. Let's say all that goes into some fancy machine, fancy lookup, converts it to a number, and that goes to a position. Now this conversion, this subject author title conversion, that's presumably fairly slow. Librarians are not necessarily looking for extreme speed in which to create that number, but we do care about this. So what I really want is you pass me some object. I have some method of converting that to a number, and that number is the position where this thing is stored. That is what a hash table is all about. A hash function. So we have, and we also, let's put this in here. And there's also hash functions. The hash table is where I store things. The hash function allows me to figure out where I store it. The hash function is essentially the thing that gives, so this is my hash function. My hash table is this here, where I'm storing it, the shelves that I'm storing it. And the reason I have a picture of a storage bin is this is my storage bin. This was a storage bin my family was using when we were moving from Boston to Ottawa. And you may not see it on this, but every single one of those boxes has, there we go, a number. Every single one of those boxes has a number because my wife was packing, has a lookup, has a would, when she was packing all the boxes, because that's sort of her wheelhouse, she's really good at that sort of thing. She was going around and every single item that she had in the house, it was the item in a spreadsheet, then the number it was associated with. Item, number. And so when we said we need winter coats because it's suddenly too damn cold in Boston just before we moved, okay, that's in box 37. Oh, we need to figure out where the coffee mugs are. Oh, that's in box 42. She found a way of converting an item into where it goes in a table, a numeric value that goes in the table. And so what I do is I have some way of converting from the item to the number. That's the spreadsheet, if you will, in this case. And that number is where it's stored. It's in box 28. So that is similar to a hash table. A hash table is slightly cleaner than that, or actually a lot cleaner than that, but it also involves a lot more math. So here is the idea. I have item 7. It's just some item. It could be a student ID, it could be anything. I'm just going to have these item classes, quote unquote, that are going to be whatever it could be any type of item. The item gets passed into the hash function. So the parameter going in is a pointer to item 7. It's a pointer to item 7. That's part of the key. That's a key part here. So the pointer to item 7 gets passed into this thing, and somehow, and it's all, voodoo. It's actually what you decide to do with this thing. Somehow I convert that item pointer to a value, some numeric value. That numeric value I want to be some value between what I need to be between 0 and 5. That's what I need this thing to be returning. So the hash function takes in an item and it spits out a value between 0 and 5. It actually spits out a value, but then you make sure it stays between 0 and 5, or 0 and 27, or however big my hash table is. It has to be a legitimate position in the table. So if you send me mail, they pass in my letter, it goes into my mailbox. Any letter that goes in has to be a legitimate thing to stick in the mailbox. Now, mailboxes are actually using names, so they're alphabetical and the like. But really, if I go back to this thing, it is you pass me in any item. If I put all my boxes in a row, 0 to I think we ended up being like 150, like 0 and 150, and you say it's in box 48, I can jump directly to box 48, open it up, pull up the coffee mugs. So the item goes in the hash, and then I need the direct line to a position. Boom. This is an array or a table, but it is something with a constant axis. It's not a linked list or something that you have to walk every element down. I jump directly to position 4 and then throw in item 7. And that's just going to get thrown in there. If I want to access item 7, if I have some way of finding item 7, I need to find item 7 again. I pass in the similar criteria, it goes in the hash function, I get item 7. This is where, like, if item 7 happened to have an ID, that's really useful. So I think in the labs we have things like a student ID, or I think it's actually open-ended to whatever you want it to be, but let's say it's a student. You have a student ID. That student ID is a number. It uniquely identifies you. So I would pass in the student ID into my hash function. It does some math, some very fast math, and says, oh, it goes over there. It goes in that position. It's a direct lookup, but sort of indirectly through this hash function. It is a redirecting function. Things go in and it gets sorted to the right place. It sorts, if you will, or not sorts. That means something very particular. It redirects. Like if I pass in a packet and it gets sent on to a particular network to go get routed to some other place. So here is the simplest possible hash function. I pass in some object O. I say object O happens to be a pointer, right? So it has an address, it is a number in memory, and I say mod whatever the table size is, in this case 6. Mod 6, and that will be a legitimate place to store this value. It is some number between 0 and 5, including 5. That's all it is. I pass in a pointer in this case, it tells me where to stick it. And we'll see why that doesn't always work for us. But for the time being, at least, that is the simplest, easiest way of doing a hash function. If I passed in a student ID, maybe I mod the table size, boom, it goes right back to a particular place in the table, right? Here's a couple other ones. So if I get the student ID and then I multiply by 491 and then mod table size, or maybe I get the student ID mod 41, mod 97, mod table size, right? It could be anything. Notice mod is really useful in this case because it gives me this sort of weird, unexpected set of results. If I mod it by some giant prime number, it gives me something. If you give me a big number and then I mod by some other relatively big prime number, it goes somewhere. I don't know what that number is. It's hard to predict. It almost gives me a random position in the table. That's what I want. I don't care where it actually goes. I need to go to the same place each and every time. I want to make sure I point this out. It needs to be fast and distributed. What I don't want is everything going to the same place on the table. So really anyway, you pass me some object or you pass in some particular value that I'm going to use for my hash function, it converts it to some number in the table. That's all I care about. Beyond that, all bets are off. You can do whatever you want with this thing. You could use the name of the person and then the student ID and then their GPA and then this and that to get the number. It doesn't matter. That's sort of the point. It's some magic secret sauce that some people may not even need to know that goes into my hash function and that spits out a legitimate place in the table. All right. Here's what the problem is. If you pass item 7 into the hash function and it says it's going to go in position 0, there's nothing that preventing you item 7 from being assigned to position 0. But item 22 also gets assigned to position 0. I get what's called a collision, and that leads to all sorts. That's the kiss of death for a hash function or in a hash table. Now, there are workarounds, but none of the workarounds are nice. So one of the workarounds, I actually gave it as an exam question last term. You won't be getting it for the exam question this term. Is you make a linked list of a hash table. So you have an array that has a whole bunch of linked lists inside of it. At each position is a linked list, and so when I add an item to the hash table, I just insert it to the linked list. So my hash table, I want to draw this thing out. My array itself is something like this. It's an array of of linked lists. So every time if item 22 is already there and I add item 7, I put the 22 in here, and I have the 7. But if worst case scenario, everything goes in the same place in the hash table, and now I just have a linked list, and that's slow again. I got the hash table and I didn't get anything for it. So ideally, what you want is the absolute minimal number of collisions. You do not want the same item multiple items or multiple things going to the same location. That means that your hash table has to normally be way larger than any amount of storage that you're going to use. You need a whole bunch of extra blank spaces. You need this to be fairly distributed across the hash table. Otherwise, bad things happen. Again, it ends up being slow. So normally you need at least twice the size of the array compared to the number of things you're going to store in the hash table. But it's constant time to get this. I pass in an item, it tells me exactly where it goes, I shove it in there. When I need to get the item, I pass in that item. At constant time, I know where to pull it out from the hash table. It is extremely fast. It doesn't get faster than this when it comes to a hash table, if you do it right. And that's the real benefit of a hash table, is that it's this really quick way of finding an item Nothing is actually faster in computer, like there's no way that we can make it faster in computer science to find a random item that you're storing into an array. If I have a normal array, what do I need to do? If I'm trying to find item 7 in a normal array and it's not in a particular order, what do I need to do? Is this it? No. Is this it? No. Is this it? No. Is this it? No. Is this it? Yep. Okay, I'm done. I have to walk down my entire array hoping I find what I'm looking for. If it's sorted, I need to do it's not constant time, but I have to go. We'll do binary search soon, but it would be, is this it? No. Is it greater or less than? Oh, it's greater than. Okay, halfway. Is this it? Yes. Right. I can slice my list in half each time, but it's still slower than constant time. HashTable is as fast as I can possibly get for finding stuff. If I need quick access, quick to be able to find and retrieve items quickly, the hash table and the hash map is really the way to go. So again, here is what my hash function looks like. It is a function. It takes in something. It either takes in the object itself or some key aspect of the object itself, and then just spits out what the index is, where in the array it goes. That's it. It sounds more complicated than it is, and then I stuff it in an array. So I have some way of mapping between an object and an index, and I have an array. That's it. And I wrap all of that up in a particular object. So I have this hash function within, and I have an array within my hash table object, right? So I add items to my hash table, and all it does is it uses the hash function, plops it in its own internal storage. No one needs to know how it works. It just has I have some magic object or class called HashTable that stores stuff for me and retrieves stuff for me quickly. All right. The quality of the hash map, though, is what kills people. In theory, hopefully it's seeming relatively easy, right? I have some fancy lookup. In theory, though, that hash quality, the quality of how I map an item to a number, that's where the problem is. Because I need to minimize the number of collisions and have an even distribution across all my table. I want everything, I want in an ideal world, every single slot in my hash table would be filled up before I have a collision. That's never going to happen, but that's the ideal world. You can custom make them, or you can make them general, so you can make it so that it takes in any old type of data, or if I know I have a particular kind of data, like student IDs from Carleton, I can make a hash function that is going to work best for student IDs from Carleton students. I can't, if you just give me a random number, it won't work, but maybe all Carleton IDs, end in the number 9. Well, I make a hash function that takes that into account. Right? Make the math work a bit better. There are lots and lots of math researchers that have spent countless hours looking at this. I cannot get my head around most of this math. You definitely do not need to get your head around this math. It is the assignment and the lab is just to have fun, right? Try something. Try a bunch of mods. Try a multiply by 272 and then mod 59 or whatever the case is. It just has to be a legitimate place in the table. And mod ends up being a really, really useful thing because it gives you sort of a randomized position in the table. That's what I want. It's not actually random. It always goes to the same place. But it means that it's not necessarily predictable where it's going to go. In fact, that's, I think, what they're actually using for most of your passwords online. That you pass in a password, it goes through a hash table. So if you type in your password, it goes to a hash table, which then actually finds your information about your account. So that one of the parts of this, you never actually put your ID, your user information, and your password together. You use a hash table so that you cannot reverse engineer it and find it easily. It gives you this level of obfuscation that information going in, I know it will go to this random place, but you don't know how it goes there, right? I put in some number, I get a different number out. I don't know how it does that, but it consistently gives me that different number out. It's a consistent but unpredictable routing. Okay, so so let me, we'll do a little pause video, stop and think part here. I said that if this thing right here, let me underline it, right? This does not work in all cases. It seems, I mean, that seems like a pretty nice hash function. Why don't we just use it all the time? So the hash function we had before is you pass in some pointer to an object. We have some table size, so all I do is take the pointer of the object, mod the table size. So it's a pointer, and I just take the address of the pointer and do a mod. And I'm going to say this is going to work terribly if I have a table size, 16 or 24 or 32 or anything like that. Numbers like that, 128, let's say. Not just powers of 2, but it will always work terribly on things like powers of 2. 60 and 64 would also both fail miserably at this sort of thing. So why is it that this does not work for all tables? If I have something like numbers like 16 for the size of my table, why is it that the pointer doesn't work for a hash function? Okay, I'll pause the video and think about it, and then we'll get back to it. I'm going to take a coffee break. Just in case anyone was still not pausing the video. Think about it. All right. The issue here is, how big is a pointer? It is 32 bits, or 4 bytes. If the address is just mod whatever the table size is, and that mod happens to be a power of, a multiple of 4, what ends up happening? It means that I will get, let's hopefully do this. I'll get stuff in here. 1, 2, 3. I'll get stuff in here. 1, 2, 3. I'll get stuff in here. I will get these bands of all values are going in these positions, but there's 3 values in between that are never being used because the pointer is always 4 bytes. So I will be skipping 3 steps in between and then putting all my information there. I'm only using 1/4 of my hash table because there's an overlap between how pointers, they're always multiples of 4, right? Or there's always, 4 bytes in between each. Because those pointers are always based are 4 bytes apart, it means that they will invariably only be stored in one of these multiples of 4 position, which means I have 3/4 of my hash table completely unused. That's why we need to get a little bit fancier with our hash tables. So what if I multiply that by 3? I take my pointer, I multiply it by 3, or multiply it by 17 or something like that, and then I do the mod. Well, I can't predict that it's going to exactly land at these positions anymore. It might land here, then here, then here, then here, all over the place. It's going to be more evenly distributed. That's the art form. Trying to figure out how to get the math working, and I'm not expecting it to be perfect, but try a couple types of hash function to see what gives you better performance, what reduces the number of collisions that you end up getting. There is no perfect hash function. You'll be lucky if 50% of the array is used at all, but we're aiming for about 50% of the array being used and not having a collision. Our hash function for the lab and for the assignment, it does not have to have that linked list thing. It's going to be an array of integers, let's say, and if there's already an integer there, don't put something in there. And just keep on putting stuff, or array of objects, let's say, and I'm just going to keep on putting stuff in there. So if I have an array of objects, let's say, or object pointers, right? So I have an array of object pointers, and I would have null everywhere. And when I finally put some value in there, I know it's being occupied, it's not null. And so I got to keep on checking each of those objects to see if it's null or not. So I try and put something in there. If it's already occupied, okay, well, I have a collision. And we're trying to figure out how many times I get a collision. That's one of the parts of the assignment. Right? And the ideal hash table has very, very few collisions. All right. We can hash based on a whole bunch of things, including the string, like alphabetical order of the strings. We can just take some kind of string and I can say, okay, the first character is going to be the ASCII value multiplied by 1,000, and then the next character is going to be the ASCII value multiplied by this, and then I can just do the math to make it work that way because ASCII values end up being or multiplied by 256, right? Every one of those things is an ASCII value, and between 0 and 255, and I just do powers, groups of that, and maybe I just do the first four characters, and that's good enough for a hash. It could be the pointer address. That's very, very, very common to the point that it's the default. The pointer address goes in. It might do something to sort of randomize it a little bit, but the pointer address is actually how it's defining where it goes. It could be some unique ID like your student ID. That's a great hash function. Anything that's unique for you means that two people are not going to go to the same place no matter what, right? Or they could go to the same place based on the hash function, but it's not because if you go off your first name, there are multiple Davids. Heck, there's multiple Davids that are professors in the CSIT department, right? The David too is also another new David as well. You can even say Davids that do game research, right? We both did that as well, right? There's a lot of we don't look nothing alike, but there's a lot of commonalities between us, right? Want something unique because if you just went off the name David, both of us would go to the same place no matter what, no matter how good your hash function is. We can do some combination of values. That is like I use my first name, my last name, and my GPA to uniquely identify me, right? You're looking for things that help describe that item as a unique thing. Or it could be the primary key in a database. That's if I have a database or something like a primary key. If you've used a database, that's ideally what we're looking for. Something that uniquely identifies that thing. That's an ideal thing to put in my hat to use for my hash, right? It's the value that gets passed into my hash function that gets converted to the position in space. All right, all that just for the labs and the assignments, and you'll be doing a hash function yourself, and I'll hopefully pass in the lab code out for you guys to play with a little bit. But I want you to try it out first because, well, it actually can come up on the exam. It did at least last year. Yeah. So let's look at templating, and this is the video that you know what I'm gonna stop it. We're gonna look at templating at another time, and we'll talk about this. Hold on.